In this video series, we'll talk about continuous probability distributions. These distributions are meant for continuous random variables. That's basically a random variable that takes on any random value between two values. So for example, between x equals 1 and x equals 2, let's just say that this is the age of a battery. Before the battery dies. Well, the battery can technically die any time between 1 and 2, not just at 1 and not just at 2. On the other hand, a discrete random variable, like the number of children that a family has, can either be 1 or it can be 2, but there's nothing in between. So a continuous random variable has infinitely many possibilities between any two values. Examples of random variables that are continuous would be heights, weights, and waiting times, like waiting times in the line of a checkout line. Previously, we've dealt with discrete distributions where the random variable, like in this case, let's say it's the d equals the number of defects in n equals 10 parts. So this company has experienced relative frequencies only up to 3 defects, no more than 3 defects. And you notice that 0.5 plus 0.25 plus 0.1 plus 0.15 equals 1. So the probabilities all add up to 1. Really, we can think about this instead of relative frequency as probability. The total probability is 100%, and here are all the possible outcomes. So this is our discrete. So n is discrete. Okay, so these bars are set up in a way to allow us to delineate the possibilities. In other words, this bar is separate from this bar, separate from this bar, separate from this bar. There's no overlap between them. There's nothing in between those two bars. And that's why we kind of press them together. Well, now a continuous random variable, let's say that t equals the time until the battery dies. And let's say that typically this battery lies between 1 and 2 years. And this is going to be now a continuous function. So let's just say that up here at 0.25, that this random variable has continuous lifespans, and those lifespans are equally likely between 1 and 2. So it's a flat line indicating that they're all equally likely. Now there's one problem. If there are infinitely many times between these, and I'll just kind of make up one big bar, imagine this is actually just a constant function like y equals 0.25. That's a constant horizontal line. And all of these values are equally likely. So okay, you might think, well, if this is going to be probability, and I want to know the probability that my battery fails 1.5 years after I've purchased it, then I should just technically be able to go over to 1.5 and look at the height at that area. Well, here's the problem. You might say the probability that t, and I'll write it this way, the probability that t is equal to 1.5, in other words, that the time until battery dies is 1.5, that probability you might think is 0.25. However, if this is a continuous function between here and here, then that means every single value would have a probability of 0.25. And if there are infinitely many values between 1 and 2, in other words, it could fail at any time, well, by the time you look at 4 of these probabilities, they already add up to 1. So this axis actually can't be probability because this is continuous. So what we call this axis is density, and we think about areas under the curve as probabilities. You might recall in calculus you did integration. Well, and that was areas under the curve. So areas under the curve are basically results of integration, but fortunately for us, we're not going to have to use any of that. Okay, so rather than to think about these points as being probabilities, we think about them as being densities. A density is just a fancy word for a value that makes the area equal 1. Okay, so let's think about this. First of all, the probability that t is exactly equal to 1.5 In a continuous distribution,